In this video, we'll be discussing motion graphs, specifically position versus time and velocity versus time graphs. For starters, you'll see a position versus time graph on your screen here. And you can also see above that this position versus time graph is meant to describe the motion of the purple car that you see here. What I would like you to do right now is pause the video and, in words, attempt to describe what the car will do as it follows along the line on the position versus time graph. Now that you've made a prediction as to what motion the car will have, let's test your prediction. I'm going to hit start here, and the car is going to move along with the motion of the graph. So you see that the car started off at 30 meters to the right of our origin at time equals 0, and then the car moved forward a bit. And as it moved forward between A and B, it slowed down. And then the car turned around and started moving backwards. At C, at D, it crossed over our origin, and then at E, and finally at F, it slowed down to a stop. Okay, so how could we have determined that based on the graph? Well, if I take a look at another position versus time graph, like you can see on the screen here, this one is maybe a little bit more straightforward than the one we just looked at. Basically, between 0 and 1 second, the position doesn't change. Our object that created this graph stays at the origin. Between 1 and 2 seconds, our object is moving away from the origin in the positive direction. Between 2 and 4 seconds, our object once again stays at the same position, but this time that position is 2 meters. And then between 4 and 5 seconds, it moves back toward the origin. And finally, 5 to 6 seconds, our object is staying stationary once again. Its position doesn't change from the origin. Looking at those time intervals between 1 and 2 seconds and between 4 and 5 seconds, we can determine how fast our object moved. We can do this by finding the slope of this graph. Velocity is the slope of a position versus time graph. That's an important concept to know. So between 0 and 1 second, 2 and 4 seconds, and 5 and 6 seconds, the slope is 0. Therefore, the velocity is 0. Let's take a look at another position versus time graph. In this one, we're asked to describe the velocity of the blue, red, and green lines. Take a minute to pause the video and for yourself describe those velocities. You should have described the blue line as having a positive constant velocity. The red line is having a velocity of 0 because its position doesn't change. And the green line as having a constant negative velocity because it has a negative slope. But what would happen if the line is curved? Well, if the line is curved, that means that the slope is not constant. When something doesn't have a constant velocity, that means that it's accelerating. So if you see a curved line on your graph, it means that our object has accelerated. That curve could curve upward, showing that it's a positive acceleration if it's concave up. And if the curve curves downward, that would show a negative acceleration or concave down. So one of the things that we can do when we have a position versus time graph is we can draw a velocity versus time graph for the same motion. That's what we'll do here. We're going back to that position versus time graph that we had before. The pretty simple motion. I've already have an axis set up here, an axis for velocity and time, but my graph is missing a few things. Think of all those things that we learned that every single graph should have. One of those things is a title. So I'm going to add a title in here. And because I don't really know much information about what created this graph, I'm going to simply title it Velocity versus Time. Another thing that's missing are numbers for my axes. I need a scale. With the time axis, you should keep the same scale as your original graph has. I'm going to put a scale on my time axis, and I'm going to wait a little bit before putting a scale on my velocity axis. I just want to make sure I don't make any mistakes. I don't want to assume I know what those velocities are right off the bat. Now that my time axis has a scale to it, I'm going to actually start drawing the graph. Between 0 and 1 second, we already talked about the fact that the position doesn't change, which means the object isn't moving. So the velocity is 0. So I'm going to put a solid line between 0 and 1 second. That was the same for between 2 and 4 seconds. This time the position is at 2 meters, but that position stays the same, which means there is no displacement or change in position, so the velocity is 0. So once again, we have a straight line on the time axis. And then the exact same thing between 5 and 6 seconds. Between 1 and 2 seconds and 4 and 5 seconds, we have to do some calculations. We're looking for the slope. The slope of a position versus time graph is velocity. We find slope by doing rise over run, or the change in the y values divided by the change in the x values. I usually like to do the later one minus the initial one. So looking at rise, this goes up 2 and over 1. And so the velocity in this case is a positive 2 meters per second. Looking at the other portion between 4 and 5 seconds, this went down 2 and over 1. So we have a negative 2 meters per second velocity for that portion of time. Before I can put those values on my graph here, I need to label my y-axis. And it's probably best to do that going up to 2 and negative 2 as the highest and lowest values on my graph. So I'm going to take a moment to label my axes. Okay, now that my axis is labeled, I can go ahead and finish drawing my graph. So between 1 and 2 seconds, we said I had a velocity of 2 meters per second, and that was a constant velocity because I had a constant slope. And then between 4 and 5 meters per second, it was negative 2 meters. Sorry, between 4 and 5 seconds, it was negative 2 meters per second. We now have a piecewise graph, and in physics, we like our graphs to be continuous. So even though it's not completely accurate, we like to put vertical lines up to connect the graph to show that this motion was continuous. So we'll add in our vertical lines there, and our vertical lines here. And we now have a complete graph. So this would be the velocity versus time graph that would correlate with the motion for this position versus time graph. Well, since we're already talking about velocity versus time graphs, we just drew one, let's go ahead and look more specifically at velocity versus time graphs. I have an example right here, and you'll see that our example has various things happening. First of all, I can tell that all of the velocities in this graph are positive. This doesn't go below the time axis at all. That tells me that the object that created this graph was always moving in the positive direction, as opposed to the previous one, which moved in the negative direction for some portion of time. Kind of like the car was backing up. Once again, if we look at this graph, we see that between 0 seconds and 1 second, our object is speeding up. It goes from 0 meters per second to 2 meters per second. And then at 1 second, from 1 to 3 seconds, it stays going the same velocity, 2 meters per second. So it's going a constant speed and in the same direction. From 3 to 4 seconds, it once again speeds up from 2 to 2.5 meters per second. And then from 4 to 5 seconds, our object is slowing down. It's going from 2.5 all the way back down to 0. It stops at that 5-second mark and stays stopped. So what information can we get from this graph other than the velocity at a specific point in time? If you said the acceleration, you're absolutely correct. Acceleration is the slope of a velocity versus time graph. So that's very important. Acceleration is the slope. You'll notice between 0 and 1 seconds that we would have a positive acceleration. That acceleration is 2 meters per second squared, because I rise 2 and go over 1. Between 1 and 3 seconds, I have no acceleration, because the velocity is constant or not changing. Between 3 and 4 seconds, I would have an acceleration of positive 0.5 meters per second squared. And between 4 and 5 seconds, I would have an acceleration of negative 2.5 meters per second squared. We're not going to draw a graph for this one, an acceleration versus time graph, for this particular scenario. Instead, we're going to do another problem, which is going to require us to take words and create two graphs. In this problem, Emma's running a little late for school today, so she decides to take I-71 to make sure she's not late. While merging on the highway, she speeds up from 20 meters per second to 30 meters per second in 1 minute, which is a really long time. She's on the highway for 2 minutes before getting on the exit ramp, where she stops at the red light. It takes her 30 seconds to stop. The entire time she's on the highway, she's driving at 30 meters per second. We're drawing velocity versus time and acceleration versus time graphs for Emma's motion. So just as we did before, we need to start off with some of the basics of a graph. In other words, we need to start by labeling our axes and giving each graph a title. Let's do that right now. So what I've done so far is I've put a title on my graph. You'll see my title is a bit descriptive rather than just velocity versus time. Since I know a bit more about what created this graph, what motion there was, I titled it a little bit more specifically, saying Emma's velocity to school. I also labeled my axes. The velocity is on the y-axis, time is on the x-axis, and I've put some markers along the way. But I have yet to put a scale on my graph. When I look back at my problem, I see that it gives me time in minutes. But just as we do for problems, we need our units to match. So since my velocity is in meters per second, I chose time to be in seconds on my problem. If I look at all the time, I see that I've got 1 minute plus another 2, so that gives me up to 3 minutes, and then 30 seconds to stop. So 3.5 minutes. That's going to help me judge how much time I need on my x-axis. And then I see that the speeds that I'm given are that she speeds up from 20 meters per second to 30 meters per second. And then she's driving along at 30 meters per second, and then she goes to a stop. So the highest my graph needs to go is 30 meters per second. I'm going to go ahead and put a scale on my graph now. Okay, so now that I have everything set up correctly for this graph, I can start putting information, start putting data on this graph. For starters, it told me that Emma sped up from 20 to 30 meters per second in a matter of a minute. We know nothing else about her initial velocity, so we're going to assume that Emma started at 20 meters per second. And we're also going to assume that her acceleration was constant. Typically, the problem will tell you that it was. This one didn't. So a straight line from 20 to 30 meters per second in 0 to 60 seconds. And then it says that she remained at that speed for 2 minutes. So from 60 to 180, we have a nice horizontal line. And then from 180 to 210, she slowed down to a stop. A nice simple graph, only 3 lines here. So this is our velocity versus time graph based on Emma's motion. Our next task is to create an acceleration versus time graph. I've already done some setup for this graph. You'll see it has a title, Emma's acceleration to school. It has axis labels, acceleration in meters per second squared, and time in seconds. And just as before, I have my time axis scaled because it's the exact same scale as we had before. But before I can put a scale on my y-axis, I need to do some calculations. I have to figure out what is my largest positive acceleration and my largest negative acceleration. And that way I can tell what scale to put on here. So let's do some math. what I'd like you to do right now is to pause the video and try and figure out the 3 accelerations for Emma's motion, from 0 to 60 seconds, from 60 to 180 seconds, and from 180 to 10 seconds. Hopefully you were able to calculate those accelerations without too much difficulty. Looking at my graph, you should have found that the acceleration between 0 and 60 seconds is 10/60ths, or 0.17, and that's a positive 0.17. Between 60 and 180 seconds, you should have found that the acceleration is 0, and between 180 and 210, your acceleration is -1. So I can scale my axis, and I know that I don't have to go any bigger than +1 or -1. Now you'll notice something a little bit different with scaling my axis this time. I did not put labels for every dash mark. You don't need labels for every dash mark. I, in general, prefer clarity. So if those numbers are getting real scrunched up, just label every other or every third dash mark. Okay, so we said between 0 and 60 seconds, our acceleration was 0.17. So this dash mark would be 0.25, and we'll be close to that, but not too close. And again, it's a constant acceleration because the slope was constant. Between 60 and 180, we said the acceleration was 0. And then between 180 and 210, we have an acceleration of -1. Just as we did when we created that velocity versus time graph based on the position versus time graph, we're going to connect our horizontal lines with some vertical lines so that we have a nice continuous graph. And so what you see here is the acceleration versus time graph that corresponds with Emma's motion as she drives to school. Let's take a look at another one of these problems. This time, Katie is running south on Kenwood Road. You can see a bunch of information about her motion. What I would like you to do right now is to draw velocity versus time and acceleration versus time graphs for Katie's motion. We will go over these graphs the next time that we have class. So make sure that you write them down so that you have something to go on as we talk about them.